In digital communication system, detection is very crucial circuit or functional block, and the detector must have some condition, must maintain some condition. Here we will try to get this type of condition, and if the detector obeys this condition, it is called the maximum likelihood detection, and that rule is the maximum likelihood detection rule. And for that, let us consider we have two symbols, say S1 and S2. Now the probability of receiving voltage V when S1 was transmitted. That is represented by conditional probability PV given S1. Similarly, for S2, corresponding conditional probability is given by V given S2, P V given S2. Also, a priori probabilities of S1 and S2 is, say, PS1 and PS2. Priori probability means the probability with which the S1 and S2 are transmitted. Now we consider decision threshold, say lambda, in such a way that for V, the received voltage, if it is greater than lambda, then symbol S1 will be selected. And for V less than lambda, S2 will be selected. Symbol S2 will be selected. In that case, the probability of error can be written as the error when S1 was transmitted and we have received a voltage less than the threshold voltage, plus the probability that S2 was transmitted but the received voltage is greater than lambda. So this is the total probability of error. Now since some voltage V is received for certain when symbol S1 is sent, we can write that V greater than lambda PV S1 dV plus V less than lambda PV S1 dV, that must be equal to 1. So if we replace this here, we can write PS1 1 minus PV/S1 dV plus PS2 V greater than lambda PV given S2 dV. That can be rewritten as PE equal to PS1 plus V greater than lambda PS2 PV given S2 minus PS1 PV given S1 dV. So the probability of error will be minimum if for every V greater than lambda PS1 PV given S1 is greater than PS2 PV given S2, or in other words PV given S1 divided by PV given S2 greater than PS2 by PS1. Now for boundary, that is for V equal to lambda, under this condition we can write P lambda given S1 by P lambda given S2 equal to PS2 by PS1. So this is the rule. Now let us try to understand it with the help of some figures. This one is the voltage. These are the mean value for two symbols. This one is for the, say, this one is for, say, S1 symbol, and this one is for S2 symbol. Now the likelihood of S1, assuming it is a Gaussian distribution, it will be something like this. It will have a peak here, and then it will follow this bell-shaped curve is there. Similarly, this one is, say, PS1 PV given S1, likelihood of S1. Similarly, likelihood of S2 will have identical curve like this, PS2 PV given S2. We set threshold somewhere here. This is the threshold. That means V equal to lambda. The error PS2 PVS2, the error will occur when we get a voltage in this region, and when S1 is transmitted we will have error when we receive a voltage near this region. With the shaded portion is actually this PE, and we get the threshold voltage expression using this relationship. So this is our rule. This is how we set the threshold voltage, and using this rule we get the maximum likelihood detection. To understand this, let us consider a numerical problem. It is said that find the decision threshold if conditional probability density functions after addition of noise are Gaussian distribution and voltage V1 represents symbol S1 and voltage V2 represents symbol S2 for no noise case. Show that threshold show the threshold when a priori probabilities are equal. For a priori probabilities are equal means PS1 equal to PS2, for bipolar signal with V1 equal to plus V and V2 equal to minus V volt, and unipolar signal with V1 equal to plus V and V2 equal to 0. So now try to solve this problem. Let us see how we can solve this problem and how we can use this relation to get the threshold. Assuming that the noise is Gaussian in nature, that is the general case, so we can write PV given S1 equal to 1 by 2 pi root over 2 pi sigma n exponential. That is a standard method of writing Gaussian function, V minus V1 whole square divided by twice sigma n square. This is for S1. Similarly, PV S2 can be written as 1 by root over 2 pi sigma n exponential minus V minus V2 divided by 2 sigma n square. This V1 or V2 are nothing but the average values. Now we replace these two equations here, these two expressions here, to get V equal to lambda. So we can write minus lambda minus V1 whole square minus lambda minus V2 whole square divided by 2 sigma n square equal to, taking the log, PS2 by PS1, and from that we can calculate the expression for lambda as V1 square minus V2 square plus twice sigma n square log of PS2 by PS1 divided by 2 into V1 minus V2, or that can be rewritten as V1 plus V2 by 2 plus sigma n square by V1 minus V2 log of PS2 by PS1. So this is the general expression of the threshold voltage for this case. Now according to the problem, we have to take PS1 equal to PS2. So if you put PS1 equal to PS2, the second term vanishes. So we get lambda equal to V1 plus V2 by 2. Now for the case of bipolar signal, V1 equal to plus V, V2 equal to minus V. So lambda equal to, for bipolar signal, lambda equal to V1 equal to plus V and V2 equal to minus V divided by 2 is there. That means it is equal to 0. And for unipolar, signal, V1 equal to plus V, V2 equal to 0. So plus V minus plus 0 by 2 equal to V by 2. So for bipolar signal, the threshold will be 0. For unipolar signal, threshold will be V by 2. So they are different. It is dependent on the nature of the signaling used or the data format is used. So this is an example or illustration how we can use this decision threshold rule, in practice.